Welcome to Back to Basics for waves, sound and light. You will have already covered the concepts involved in the previous Back to Basics lesson, but let's revise some of the trickier calculations you might face. The wave equation needs the velocity v, the frequency f, and the wavelength lambda to be in the right units. The velocity of waves is simply referred to as the speed, as the direction of the waves in the equation is not taken as a vector. This must always be in meters per second. The frequency should be in hertz or seconds to the power of -1. Lambda, the wavelength, should always be in meters. So how does that look in a typical question? Let's use sound, because most of the Doppler questions you'll face involve sound. In this example, sound is said to be traveling at a set speed of 340 meters per second. If the wavelength of the sound waves is 2 centimeters, what is the frequency? When substituting into the equation, the velocity of the waves is already in the correct units. But we notice that the wavelengths needs to be in meters, so 2 centimeters is 0.02 meters. When we solve the equation, we see that the frequency of these waves is 17,000 hertz. That's very high and almost too high for human ears to hear. We are limited to sound that can be transmitted and detected in our inner ear, and the wavelength of the wave determines the objects that they can interact with. Most humans can only hear up to 20,000 hertz, but animals like dogs can hear frequencies much higher. What about light and other electromagnetic waves? While it's unlikely that you will encounter these type of calculations in the Doppler section, it is important that you see light or electromagnetic waves as any other. They're just waves with frequency, wavelengths, and velocities that can be measured. The special thing about light is that it doesn't need a medium to travel in and moves at 3 times 10 to the power of 8 meters per second, a constant we call c. When we are asked about the wavelength of a radio wave with a frequency of 100 megahertz, it's difficult to know how to calculate the wavelength. The trick is the speed. The speed of light or any electromagnetic waves is usually assumed to be that constant c. That's written on the data sheet as 3 times 10 to the power of 8 meters per second. When you substitute, remember that the frequency itself must be written in hertz, not megahertz. So that means 100 times 10 to the power of 6 hertz in the place of frequency. Solving for wavelength means that it equals 3 times 10 to the power of 8 divided by 100 times 10 to the power of 6. That leaves us with a large wavelength of 3 meters. This is a radio wave, and that is why cars need relatively large antennas to receive these waves. Now, could you predict what would happen to the frequency if the wavelength would be halved? Could you do it without calculating it? If we see the relationship between wavelength and frequency, they are inverse. So, if I halve the wavelength, I double the frequency to 200 megahertz. Even if that last question was a little tough, don't worry. It's all about practice, and waves will be the part of the physics you look forward to.